Hi folks, this is Mr. Pinola, and today we're going to discuss a little bit about how electrical energy gets from a power plant to our house. On the screen right now, you see the path that electricity takes from when it is first generated to when it arrives at your home. The generation of electricity happens at a power plant, sort of like the one you see roughly pictured here. But how does that actually occur? Let's take a closer look. Well, before we understand how electricity is generated at the power plants, we need to understand a little bit about the connection between electricity and magnetism. A couple weeks ago, we discussed a process called electromagnetism, in which you did a little animation online and discovered accidentally, in much the same way Hans Christian Ørsted, a famous Danish scientist, did, what the process of electromagnetism actually looks like. If you take a look at the animation on the right side of your screen, you'll see a person that is connecting an electric circuit. And whenever they make the connection, the compass spins. When they disconnect the circuit, the compass goes back to pointing the normal direction. Watch that a couple times and you'll see that happening. Anytime the circuit is closed and current is running through the wires, the compass flips. And that's because the compass is sensing a magnetic field. This is called electromagnetism. It is the idea that you can use electric current to generate a localized magnetic field. And this is a key component in how any kind of electric motor will work. Perhaps an electric motor in your car, or an electric motor that might operate a battery-powered fan, or anything of that sort. Basically, in any kind of electric motor, you need electromagnetism to happen, where you flip a switch, turn on some current, that creates a magnetic field, and it might cause something to spin as a result. And once again, as we said, this was discovered accidentally by a man named Hans Christian Ørsted. However, electromagnetism can be reversed. Let's take a look at what I mean by that. There is also something called electromagnetic induction. And this was hypothesized by another scientist by the name of Michael Faraday. If you take a look at the animation on the right side of the screen, this is showing electromagnetic induction. Notice that when the animation starts over again, there is no water rushing from the faucet and the magnet is at rest. Now the water is turned on and the magnet spins. And as a result, the light bulb goes off on the right side of the screen. Now notice what's happening. When the magnet was still, there was no electric current in the nearby wire. But when the magnet was moving, all of a sudden now, there's current nearby. This is a case of magnetism creating electricity, almost the reverse of electromagnetism, in which electricity created magnetism. However, this one's a little bit more complicated, because notice that just by holding the wire still, there was no current. See, still magnet and no current in the wire. However, the magnet has to be moving to generate the current that will turn on the light bulb. And so the reason this is that Faraday discovered that you need a changing magnetic field to generate electric current. Notice that whenever the magnet spins, this nearby compass keeps spinning around, showing that the magnetic field is constantly changing direction. As long as the magnet is moving, there will be current in the nearby wires. So whether the magnet is spinning, whether it's moving back and forth, up and down, as long as the magnet is moving, then it's going to create current in the nearby wire. And so this is a case where you now have magnetism creating electricity as long as the magnet is put in motion somehow. And this is what happens in a generator, which is a device that uses this idea of getting magnets to move and generating electric current. So, this paddle wheel that you see right here is basically a very simplified version of what's called a turbine. And a turbine is basically any kind of device that's attached to an axis that has a magnet on it. And anytime you get a turbine to spin, you can spin the attached magnets. And if you happen to have coils of wire nearby, these coils of wire are called solenoids. Maybe you've heard of that before. If you happen to have a turbine with an attached magnet, and the attached magnet spins or moves, whether it's back and forth or spinning, near a coil of wire, you're going to generate electricity in that wire, even if the wire isn't attached to anything. So, as long as we as humans can find ways to spin the turbine, we can generate electricity. This is an example of how you can take moving water, just like in this picture, spin the turbine, and generate electricity. This is called hydroelectric power and is used at large dams, for instance, at Niagara Falls. At Niagara Falls, when the water comes down, it will, in some cases, hit small paddle wheels and it will generate electricity in nearby substations. That's an example of using water to generate electricity. This can also be done with wind. Maybe you've seen giant wind turbines. When the wind hits these huge-looking windmills, it spins a turbine, which is what you see from the highway, and that turbine is usually attached to a magnet, which is going to create electricity in nearby coils of wire. You could also get steam. For instance, if this faucet were turned off and there would be something burning from the bottom, the steam would rise up and it would also spin the paddle wheel when the rising steam contacts the paddles of the wheel itself. You could burn anything to get steam, and so we'll talk about that a little bit more in a second. So, really, to generate any kind of electrical energy at a power plant, you just need to find a way to constantly spin a turbine like the one you see on the screen, because then by the process of electromagnetic induction, you will get the magnet to move and you will generate electric current in a nearby coil of wire. So, as we said, we can do that with moving water using hydroelectric power. This was done back in the early days around the Industrial Revolution. They used a lot of hydroelectric power to spin turbines, and you can see another example of it here. This can be done using wind, which perhaps is the most intuitive way to do it, and you've also seen those giant wind turbines. And it can also be done by steam. For instance, if you burn coal, that's a common way to generate steam and spin a turbine from the rising steam. You could also burn natural gas. You can also burn oil or petroleum. And that's why these resources such as coal, natural gas, oil, that's why these are so in demand, because they can help us generate steam, and that will be burned to create energy, electrical energy at power plants. And these down here are considered fossil fuels. They are non-renewable resources because when we burn them, we use them up, as opposed to moving water and wind, which are renewable resources. Once you use them, you can certainly use them again. The water doesn't go away, the wind doesn't go away, as the coal, natural gas, or oil might. Now, there are also other ways to generate electrical energy that go a little bit beyond the scope of this course. For example, we'll talk about nuclear power, in which you need to have samples of radioactive material. Nuclear energy is an example of a non-renewable resource, because once you use up the nuclear samples, you can't get those back. But that's another way to generate energy. And also there's solar energy, which perhaps you've heard of. Solar energy also works a little bit differently, but it is renewable. And so that is a renewable resource because you can still get the light from the sun. We'll also talk briefly, as you read another article this week, about biomass and geothermal, which are other ways to generate electrical energy at power plants. But hopefully this gave you a good description about how electrical energy is generated at those power plants before it is sent out to our home. The next video is going to focus on what kind of journey does that electricity take between the power plant generating station and when it arrives at our home. Until then, take care.